104C at the University of South Florida, Stratigraphy and Paleontology, and this is Sarah Sheffield. So today is going to mark a 2-day lecture into sequence stratigraphy. This lecture is going to focus on the facies and the rock stacking patterns, what sequence stratigraphy is, and what it can tell us about Earth in the past. The next lecture is going to focus more on how we can use fossils to help us identify sequence stratigraphic patterns, which is super cool. All right. So first off, sequence stratigraphy can sometimes be a lot to learn. There's a lot of new vocabulary. It's a new concept. It's totally manageable. It's absolutely doable, and it's really fun to learn about. But if you need extra help, SEPM, which is the Sedimentology Society for Geologists, there's a lot of playlists that can walk you through a lot of this. So use those extra resources if you need them. The SEPM site is a goldmine of educational resources for sequence stratigraphy. So there's a bunch of new words we're going to be learning today. Some of these might be familiar to you. Others may not be, but they're pretty intuitive. So don't get too worried about that yet. All right. So first is going to be progradation, meaning a building out of the shoreline. The shoreline extends further out. This is going to go hand in hand with a regression. All right. So a low stand is low eustatic sea level fall. All right. Moving towards a progradation. Retrogradation is a flooding of the shoreline, so the shoreline actually retreats towards land. That's going to go hand in hand with a transgression. And a high stand is going to be a high eustatic sea level. We'll talk more about these terms a lot later. And then finally, systems tracks, a series of depositional features that represents periods of high stand, low stand, regression, transgression, progradation, and retrogradation. All right? So sequence stratigraphy. This is what it looks like. I know, it doesn't look like much right now, and that's okay. Or if it does, it looks something like we never want to look at it again. Don't worry, all right? So what we're looking at is a combination of a lot of different sciences. These advances to come up with the science of sequence stratigraphy came from seismic stratigraphy, as well as sedimentology and other arenas, all right? So these were created using seismic profiles. So we would shoot little laser guns down into the sediment, all right? And the time it takes for those seismic reflectors to bounce back can tell us a lot about the different density. It can tell us about the different surfaces, which helps us create a picture of what's going on inside the Earth, all right, but below our feet. So here we see a number of different depositional environments: alluvium, a river, near shore, marine shale, proximal fan, and basement. All right, there's the basement. And what we see is a vertical stacking pattern that changes, right? That's Walther's law. We know environments that extend horizontally stack vertically in the rock record. And what we can see is that there's changes through time. So at some point in time, the marine shale extended a lot further inland than it did a little bit later, right? So we see too that rivers once extended really far out there. So this would have been a time of massive regression, or what we would call progradation, where the shoreline is extending further out because the sea level is falling. So we can actually do some really interesting science with understanding how paleo environments have changed through time using this science. Now, this was developed primarily by someone named Peter Vail in the mid-1970s. He worked for an oil company, and this was kept really hush-hush for a long time. And the reason why is because other oil companies they didn't want other oil companies to know about it. Why, though? Why would this be helpful to oil companies? Well, it tells us a lot about changes in accommodation space and sedimentation rates, tectonics, and sea level change, all of which can tell us what areas of the world might be more likely to hold oil and gas than other areas. We know that accommodation space, tectonics, and sedimentation rates can tell us a lot about areas that might be more friendly for hosting large bodies of natural resources. So oil companies find sequence stratigraphy incredibly useful. And in fact, if you go into the oil company, sequence stratigraphy very might well be a skill you were expected to learn. All right, so sea level changes through time. It rises and it falls naturally. Why? All right, could be changes in crustal uplift, used to see. Could be changes in glacial ice, Milankovitch cycles, changes in accommodation space. So all of these can happen naturally. Some of these can happen in conjunction with one another, like Milankovitch cycles can influence glacial ice. Glacial ice, the more glacial ice there is, the harder it is for crust to uplift, right? Because it's weighted down by the glacial ice. So all of these can kind of blend into one another. But the thing that we need to know is that sea level fall and rise happens naturally through geologic time. There are areas where sea levels are much higher, areas where sea levels are much lower. All right. And of course, this all varies across the globe too. There are basins that are in sea level rise and sea level fall at the same time in different parts of the world. So sequence stratigraphy is an ideal model of deposition during a complete base level cycle of rise and fall. Now, we're not necessarily concerned with the absolute amount of water, the depth of water. It's not really something we can get at either. We can have some pretty good guesses, but the absolute amount of water is going to be pretty difficult to measure. What we're concerned about is relative rates of change. So relatively where it's rising, relatively where it's falling. And the reason for that has to deal with accommodation space and sedimentation. All right, that's going to be the more important point here than just absolute water depth. And we'll talk more about that in a little bit. So the fundamental control here on the depositional sequences and the formation of these sequences, the preservation of these sequences is going to be accommodation space. Quite simply, how much room is there? So that's a pretty important control on this particular point. So it's going to be kind of a combination of use to sea, subsidence, and climate. All right, and we're going to call this base level, and we'll get back to that in just a second. All right, climate is going to be the least important of these factors typically. So this is going to deal, there's two types of accommodation space we'll talk about. First is fluvial, so river accommodation space, and marine accommodation space. All right, so marine accommodation space is this between seafloor and base level, So seafloor and base level, this is the accommodation space. This is it. This is all the space you have to work with. For fluvial accommodation space, it's much smaller. All right, and it's going to be the land surface profile and the graded profile, which is why understanding the graded profile of rivers is so important. So the more siliciclastic sediment coming in to an accommodation space or into the marine, we're actually going to be filling that accommodation space. If you imagine if we dump a whole bunch of sand in here, we raise the sea floor, we're going to be reducing accommodation space without ever changing the sea floor or the amount of water. Does that make sense? That's why accommodation space is really what we're focused on instead of water level itself. So here are some terms. We've gone through them, but we're going to go through this again. First, aggradation is building upward. Incision is eroding downward. We care about this because things erode to base level. Rivers erode to base level. We've talked about this before during our river geology lectures, and you've probably learned a little bit about this during earlier classes in geology, but rivers erode. That's what they do. All right? So rivers will erode to base level. So if the sea level falls and retreats, rivers will continue to erode out to meet that base level. So that's why understanding base level is so important. All right, so transgression again is a retreat landward, meaning the ocean is moving up. All right, and regression is building seaward, that ocean is moving backwards. So this is going to go with the terms that we've just learned for progradation, that goes with regression. Prograding coast goes with a regressing sea, and a transgressing sea goes with a retrograding coast. Now, the important thing here is what we're looking at is the stacking of facies patterns, the vertical stacking of facies. So if we see fluvial rocks and then beach rocks on top of it, and then deeper ocean rocks on top of it, we can assume that the oceans have been transgressing and the coasts have been retrograding. If we see the opposite, if we see open shelf on the bottom, then shore face, beach, and then on top fluvial, we can say that it was likely that the sea was regressing and the coasts were prograding. All right, so that's how we're going to measure our sequence stratigraphic changes through time. So here's what that's going to look like. Again, it's going to give us a vertical stacking pattern of facies. We're going to read this from bottom to top, so superposition. And again, this is going to deal with Walther's law of facies. The horizontal distribution of facies will stack vertically in the rock record. So here is what our model of base level change is going to look like. All right, so we have our sea level rise, or base level rise, base level fall, base level rise through time. Now, this is an idealized model, and we'll say this again at the end to make sure you understand this. What that means is it's pretty much never going to look this beautiful in real life. It's never going to be this symmetrical. We're typically never going to see a full model of base level rise and fall through time. All right. So what we're going to look at here is what we see are times of sedimentation rate being positive and sedimentation rate being negative. Here we have sedimentation rate being positive, so this is a grading through time. We'll also see it being negative, which is right here. This is where it's going to be incising. All right. Typically where it's going to be incising, we're going to see some erosive surfaces as well. So again, regression and incision are going to happen during base level fall. This is where we're seeing regression and incision. All right, during times of sea level rise, where I've got these blue squares here, this is going to be transgression and aggradation. Now the rates of which are going to change. There'll be times of higher transgression and higher regression, as well as lower transgression and lower regression. All right. So at some points in time, even during base level rise, if we still have sedimentation stacking, or if we have too much sedimentation happening too fast, we can still have it looking like a regression, meaning relative sea level fall. That's because there's two different types of regressions. All right. There's a normal regression, and that's when there's more sediment supply outpacing base level rise, meaning we're pouring more sediment into the basin than the water level is rising. So if you imagine with me, let's take a jar and we're going to fill it with marbles halfway through. All right, so let's put some water in there. We'll take half marbles, half water. Okay, if we start dumping marbles in there, even though it's full already, we're going to be that water's not really going to be changing much, right? We're just going to be making less room for it. So that's what's a normal regression. We have more sediment coming into the system than water level is rising. Okay? So that's still going to be a regression. It's just going to be what we call a normal regression. That's going to be to the opposite of a forced regression, where the ocean level is falling. Okay? Ocean level is falling. This is typically going to be seen with like a massive glaciation or something like that. Okay? Coastline is forced to regress. Does not matter how much sediment is going in there. And with regression, we typically have increased amounts of erosion, so there is sediment going into the basin. It's just that sea level is falling faster. All right? And then transgression is going to be, again, that sea level rise. So fundamental concepts. This is going to be where a lot of our terminology comes into play. So don't get too hung up on the different words. It's going to take you practice to get used to using them, and that's okay. That's why we're here, right? So what you're going to do is you're going to do multiple in-class assignments on this particular topic because it can take a little bit of practice using these terms. So our sedimentary successions are divided into what we call unconformity bound units, otherwise known as sequences. Our sequences are bound by unconformities. This is essentially what one cycle of sea level rise and fall looks like. Now, each of our sequences can be divided into smaller units, and they're recognized by our vertical facies stacking patterns, just like we've talked about. Now, you'll notice that sea level rise isn't continuous. And what I mean by that is here we have sea level rise, fall, even though it's gradually rising and gradually falling. That's because there's a number of smaller global cycles in play. For example, Milankovitch cycles can often cause some of these smaller changes. So even though it's a general sea level rise, there will still be smaller waves of sea level rise and fall within it. Okay? All right. So here we have our sequence. All right. It is bound by unconformities. So there are unconformities on either side of this. And this sequence is composed of a number of linked depositional systems that we're going to call systems tracks. So within one sequence, we have systems tracks, things that show regression and transgression. All right, and again, this is going to be deposited between eustatic sea level fall inflection points. So we're going to see multiple sequence tracks, or systems tracks, in one sequence here. And this is, again, what that looks like. I'm going to keep showing this graph to kind of make it a little bit more clear. So we have unconformities kind of bounding here. So we have sequence boundary 1 and 2 here. All right. And what we have in between, we have things like the transgressive systems tract, showing where one of the sequences that we'll see. We also have something called the maximum flooding surface that we'll talk about here in just a second. All right. So we're going to go back to this real quick. Again, depositional systems. So one sequence is made up of systems tracts, and then we can find smaller units. These are the smallest facies unit in sequence stratigraphy, called parasequences. All right. These are related beds that are bounded by flooding surfaces. For example, the maximum flooding surface. This is the deepest point in a sequence, all right, as it sounds like, the maximum flooding surface, and it's evidence of an abrupt increase in water depth. And we'll talk about how we know what that looks like here in just a second. But here we have one of our systems tracts, the high stand systems tract, the HST, the transgressive systems tract, the TST, the low stand systems tract, the LSST, and the falling stage system tract, the FSST. I know, it's a lot of abbreviations, but better than saying them out loud all the time. All right, so we have our maximum flooding surface when there is the highest point of transgression. We also have the maximum erosive surface, right, or maximum regressive surface, otherwise known as the ravinement. There's a whole bunch of different names for it to show the shallowest point as well. Those are our parasequences. And those exist along with our systems tracts. They are in our systems tracts that make up one sequence of sea level rise and fall within a basin. So here's this again. We have our systems tracts highlighted with a circle, the TST, the transgressive, the HST, the high stand, LST, the low stand. We're missing the falling systems tract right here. We have our parasequences highlighted right here. It's just the flooding surface in this particular area. But what you see is this is correlating with the different facies patterns. So we have a facies of submarine fan all the way down here with the low stand, indicating essentially the shallowest that ocean's going to go, maximum regression at this point in time. We actually have submarine fan exposed in this particular area, all right? As opposed to where the flooding surfaces are going to be, we're actually going to see the marine surfaces coming up into the coast, almost all the way up to the coastal plain. So that's how we can see what's going on. Vertical stacking of facies can tell us about those shifts. All right, so let's take a deeper look at these systems tracts. Again, here are the 4 systems tracts. Here are their abbreviations. You are welcome to refer to them by their abbreviations. As long as you're using the right one, I'll know what you're talking about. Here is a video showing how this is actually happening. This is by Mino Savani. Thank you very much, Mino. All right, let's hit play on this. So what we can see is how changes in relative base level are actually causing the building. You can see those here. All right, so it's moving through. There's an orange arrow right there. And we're moving into the transgressive to the high stand systems tract where it's getting pretty high. Now it's starting to fall again. From a falling stage systems tract, you see that the coast is prograding through a regressing ocean. The low stand is about the lowest it's going to get. You see those deep incisions from all of the erosion, right? Rivers eroding to base level. We see now that it's transgressing again, hitting the maximum flooding surface. Now, there we go. That's the highest it's going to get. And then it will slowly start to fall again. We have a little boat out here that I just noticed kind of chilling in the middle of all of this. All right, so definitely watch this again, but do you see is how the more shallow we're getting here, the more the coastline is prograding out. We see these rivers are incising more and more. They are eroding to base level, and there's a lot of sedimentation going into there, which is affecting the normal regression that we just talked about. Now, this is clastic systems sequence stratigraphy here. Carbonate sequence stratigraphy is actually pretty different. And it's not going to be covered in this particular class, but you should know that it is definitely still a thing. All right. So how do we know the depths of all these systems? As we talked about, seismograms. So here we have our travel time. All right. Seismic waves are sent out, and every line here is a reflector showing some kind of difference, right, in density. typically. All right. So the time at which it takes can actually be converted back to depth, and it can tell us a lot about the different boundaries and reflectors inside the Earth, so what we cannot see ourselves. And that's how we actually create things like this. We can understand internal relationships. We can see the unconformities that are sequence boundaries. We can see different surfaces here. Now, top lap, on lap, and things like that. These are just the angle at which things are essentially meeting each other, how different beds are hitting these sequence boundaries. We're not going to focus too much on that here. All right, so let's look at this. High stand systems track. It is going to start here with our maximum flooding surface. After this, base level will start to fall. Here we have it, the high stand systems track right here. We can see the rates of base level change. At this point, we are still positive. Okay, sedimentation. So sediment supply is going to start to outpace base level rise. All right, which means at this point, we're going to start prograding the coastline. The coastline's moving out. We're going to start moving into the regression. Okay, so we start with that maximum flooding surface. That's the highest level that it will ever be, and it immediately start falling after that. So even though for a while it looks like it's getting a little bit deeper, that sediment is starting to outpace sea level rise. So we will start to move into a regression at this point. So what we'll see is a vertical stacking pattern showing a shallowing up, meaning it's getting shallower. It's prograding. Okay? So here we have our falling stage systems track. What we're going to see is that base level fall is going to start moving faster and faster through time. We're moving into a massive regression. We're moving into negative sedimentation rates. All right. And typically what we're going to see is a lot of unconformities in this particular area. FSSTs and LSTs are actually a lot less common to find in real life, and that's because of all the unconformities and the erosions. All right, the erosion. Excuse me. So base level fall is going to increase. The rate of it is increased. Typically, this is going to be forced regression here. So the coast is building outward into the basin. Sea level fall is happening. It does not matter how much sediment is piling into that basin. Sea level is falling, as opposed to a normal regression where it's mostly just concerned with the sedimentation. We're going to start to see wave-dominated coasts forming, where at one point in time we had deeper waters, and this is going to create an erosional surface that's going to mark the boundary of our FSST into the low stand tract right here, the LST. So at this point, rivers are going to continue to incise into the marine shelf, forming valleys, and they're going to get bigger, and they're going to grow landward and seaward as well. So rivers really erode to base level, as I've said multiple times throughout this lecture here. And what this means is that we're going to have active sand deposition into the deeper basin, the submarine fans. The submarine fans are going to be the least likely to actually preserve. We typically do not see them. And again, that's going to be because of a lot of that erosional surface there. But when you do find them, you know that you're in that low stand. Okay, so the LST is that maximum regressive surface, otherwise known as the ravinement surface, or the MRS. You can call it a whole bunch of different things. It's the maximum prograding of facies. Okay, remember, progradation goes with regression, just as retrogradation goes with transgression. So that low stand systems track is when that base level is going to slow way down. Sea level fall is going to be exceeded by subsidence, and all right, so we're going to have more sea level fall there, and we're going to see a very, very slow level rise in base level. Okay, so it'll start to go up just a teeny tiny bit. Okay, so this is going to be the greatest extent of subaerial exposure and erosion. Okay, now is when we start to flip to our transgressive sequence track. What we're going to see is sea level rise is going to start outpacing sedimentation. So water level will get deeper no matter what. All right. And at that point, we'll see the boundary here, that ravinement surface here. So where the erosion is forming during that original sea level rise. And we're going to continue till we get to the maximum flooding surface. So we're going to start to see a retrogradational parasequence stacking. Again, what that phrase means, because it sounds like a load of hooey for those of us just getting into this, right? It means that the water level is getting deeper, and we're going to see a vertical stacking of facies there. So we're going to go from shallower water facies to deeper water facies on top. Okay, so we're going to see the development of flooding surfaces. All right, so we have our first flooding surface, which is the transgressive surface. It's going to lay over that low stand to transgressive stand. It's going to be a erosive surface at this particular point. All right, so we're going to see alluvial, coastal plain, shallow marine, not going to see submarine fans at this point in time. All right, here we have our transgressive sequence tract again. We are in a mark of transgression. Maximum flooding surface is the parasequence boundary between TST and HST. So sea level rise is going to start to slow at this point. You see how it's starting to slow. All right, and then it's going to even out. This point right in here is our MFS, the maximum flooding surface. Once we get to that, we're going to switch from retrograding, meaning the sea level is getting deeper, to prograding. Sea level is getting shallower and the coast is starting to extend out further. All right, so as you see, this is again all relative. It's not an immediate flip. We see that the level of base level changes, rising and falling, definitely slows down at these maximum points of inflection, either at high sea level or extremely low sea level. Now again, these are idealized models. It does not always look symmetrical. It is not always as beautiful, nor does it typically show every stage, every erosive surface, every flooding surface. We rarely see every stage, really. We can use other lines of evidence to go with this as well. So we're not just relying on vertical stacking. We're looking at facies, we're looking at sedimentary structures. We're looking at fossil clues. We're looking at seismic boundaries. This is a massive science that takes a lot of other geologic intuition to fully build sequence stratigraphy models. Now again, it does also not have to happen at the same rate in every part of a basin, right? This is not happening all over the world at the exact same time. Variance is expected. All right, and this is again, just one last look at this. This is exactly what's happening. These sequence boundaries are showing us the boundaries between these sequences where we see sea level rise and sea level fall. And last but not least, we're going to take one more look at this again. What we're looking at here, all right, is what we're looking at is one sequence of sea level rise and fall. We have a systems track here. All right, we have our boundaries. We're looking at this by understanding the different facies stacking patterns, and that's what you're going to be working on in conjunction with this lecture, facies stacking patterns. All right, so if we're starting off in shallow, right, we're probably going to see some form of a fluvial system in this particular case. If it's getting deeper, we'll see coastal system stacking on top of it, and then a shallow marine system stacking on top of that. If we are regressing and the coast is prograding, we'll flip this upside down. All right, here are your review questions. We will reconvene with sequence stratigraphy part 2.